Hey, my name is Rishi Patel, and this is my Physics 2212 Lab 5 video lab report. The purpose of this lab is to use principles of Faraday's law and the time-varying magnetic field to predict the time for a magnet to fall through aluminum foil. In addition to this, the observed data will be compared to the computational model. In this PowerPoint, I will go through the introduction, fundamental concepts and principles, the experiment, computational models, and also the discussion. The overall result is that the time predicted by the model is 1.09 seconds. Fundamental concepts and principles are Faraday's law, Ohm's law, Lenz's law, and also the magnetic field of a bar magnet. The procedure for this experiment is as follows. First, we must measure the physical properties of the aluminum foil and magnet, which includes the length, width, and inner radius of the aluminum foil and also the mass of the magnet. Then, we must drop the north end of the magnet down the aluminum foil and record the time it takes to reach the bottom. This is going to be done for 5 trials, and then the average time will be computed. Why can't we use a ferrous tube, for example, a steel pipe? Well, ferrous tubes contain iron, which is an element that has ferromagnetic properties. The tube may become an induced magnet, which will affect the falling magnet overall. What happens to the magnet? How does this compare to a falling magnet in free space without a tube? The magnet slowly falls through the tube in the experiment. If the magnet fell in free space, it would fall much faster. Here are the physical properties of the aluminum foil and magnet. The magnetic dipole moment here is found from lab 3. The average time taken for the magnet to reach the bottom of the tube is 1.232 seconds. The following slides will outline the computational models and the steps within it. The first step of the model lists the geometry of the tube and also the properties of the magnet. The last few lines of code creates a visualization of the bar magnet as it falls through the tube. Step 2 of the model calculates the magnetic field of the bar magnet based on the mu and r values given in the function. Step 3 of the model calculates the change in flux through each ring due to the falling magnet. Step 4 of the model calculates the current in the ring and also creates a color visualization of the ring as the magnet falls through the tube. Steps 5 and 6 calculate the typical magnetic field at each ring. The first part of step 7 calculates the force due to gravity based on the mass of the magnet. The magnetic force from the tube on the magnet is also calculated along with the change in flux for a ring due to the falling magnet. The second part of step 7 calculates the net force due to the force due to gravity and also the magnetic force. The final step of this model uses the magnet's velocity to create a graph of velocity versus time for the magnet as it drops. These are the computational model results. As you can see, the time it took for the magnet to reach the bottom of the tube was 1.05 seconds. On the left, we can see a model of the aluminum foil and also the magnet as it falls to the bottom, and also on the right, we can see the velocity versus time graph. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing opposite directions. Which color corresponds to the clockwise current and which color corresponds to the counterclockwise? How can you know? Well, red corresponds to counterclockwise and blue corresponds to clockwise. This makes sense because this is how the magnet would slow down as they are in opposite directions. What happens to the dynamics of the system when you flip the magnet around? Flipping the magnet would yield the same results, but the currents would be flipped. How does the total time in the tube of your real-world system compare to that of your computational model? Well, the time taken versus the time from the computational model is fairly off. The results were not very accurate. How might the computational system be made more accurate? The model could account for air resistance, and more rings in the tube may create more accurate results. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The forces are not balanced in the first part of the graph, but the forces are balanced in the middle part of the graph and is once again unbalanced at the end of the graph. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If this were the case, the induced current would be very big. As a result, the magnet would fall through the tube much slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The current will be disrupted and there will be a reduction in induced current. This in turn reduces the magnetic force, which means that the magnet will fall through the tube much quicker.